Hello, I welcome you all in this presentation related with the subject failure analysis and prevention. And we are talking about the failure analysis of the components manufactured by the forming processes. So, in this particular presentation basically I will be talking about the cracking tendency observed in high strength steel which was being used for manufacturing the pipes. Okay. So, let us go failure analysis of the high strength steel pipes in course of the manufacturing. So, as far as the potential causes are concerned, like obviously the cracking is taking place during the manufacturing means there is a embrittlement or there is a limited ductility of the material. So, material may have quite good ductility, but in course of manufacturing also it can get embrittled due to the multiple reasons. So, what failure analysis procedure was followed that included like composition analysis, microstructure including XRD analysis, mechanical properties and non-destructive testing of the steel plate which was being used for fabrication of the pipes. So, relevant findings and the observations. Okay. So, the issue here which was encountered was basically during the manufacturing of the large diameter pipes, the process of the rolling and the welding is followed. Okay. So, basically very large sheets are used and they are rolled in very controlled way. Okay, like this, and at the end we find that the after rolling a shape like this is obtained. So, here the joint is made at the end. So, for this welding is needed and for rolling the sheets and giving the shape like a pipe, the rolling process is used using the steels. So, what had happened like during the rolling to give the shape to the plates as per the requirement of the pipe in the desired diameter, the cracks were observed. So, this needed like the investigation, what would be the reason behind the cracking of the steel plates during the rolling process, and thereafter of course during the welding another kind of the problem was observed. Okay. So, the method which was being used like the rolling of the like the steel plates, rolling of the steel plates. So, depending upon the requirement, the plates were like 5 to 25 in thickness, especially in large diameter the problem was more severe as far as the cracking is concerned. But since the steel plates need to be prepared first in as per the required size. So, for that the steel plates of the desired size were obtained through the cutting process. For the cutting variety of the approaches can be used which can involve like the mechanical cutting involving shearing, it can be thermal cutting using plasma or laser, and chemical cutting using for the heavy sections is not that much used at the commercial level. So, when the mechanical method is used for cutting, the cutting edges are not much affected in terms of the properties or property modification. But when the thermal method of the cutting is used for, then the thermal method modifies the structure and properties to a great extent. Of course, it will depend upon the metal which is being processed. So, if the steel plates are of the high carbon equivalent like say greater than 0.3, means the steel, this will be making steel little hardenable. If it is 0.5 or more, it will be very hardenable. So, on thermal cutting these hardenable steels will show a lot of increase in hardness, reduction in ductility, reduction in toughness. So, that we can say in terms of embrittlement. So, steel gets embrittled when thermal cutting method are used, especially in high hardenability steels or high carbon equivalent steels. Okay. So, when the steel plate of the desired size cut by the thermal cutting methods, okay, was getting hardened, and later on this was being used for the rolling purpose to give the shape like a pipe. So, it was showing actually the cracks on the outer periphery. Okay. So, this was required, like what would be the reason behind. So, cracking during the bending for forming the pipes were observed. So, in the next slide what we can see is this is the like typical approach of making the large diameter pipes, where we can say the steel plate is getting deformed in very controlled way to take the shape like a large diameter pipe. Thereafter, these are welded. So, this is circumferential weld, and then welding will be done along the length of the pipe also. Okay. So, there will be two types of the welds. One is longitudinal along the length, because say after deformation we have got it like this, then the weld is to be made all along the length. So, that will be the longitudinal weld, and when there are number of pipes which have been made, then to obtain the desired length of the pipe in continuity, again the circumferential welds are made. So, the pipes need to be reconnected circumferentially. So, this is an example where the circumferential weld is being made. Okay. So, this is the typical approach of making the pipe which is used. So, initially efforts were made to come out like what would be the typical regions for the cracking of the pipes during the fabrication. So, it was found that it is possible like in steel in very localized way, having the very limited ductility. Okay. So, if the steel normally say having 10 or 15% ductility, but in localized manner due to the heterogeneity of structure composition, this may show like a 5% ductility also. So, this we can say as a anisotropy or heterogeneity in properties, non-uniformity in properties due to the multiple regions, which can be microstructural heterogeneity or chemical heterogeneity. So, the one of the regions which can be there is like limited deformation capability under certain directions. Okay. So, you know the steel plates usually made by the rolling. So, there are multiple directions lengthwise, the perpendicular to the length, and then in thickness direction. So, these are the three most common ones. So, it is possible like metal can show the lot of variation in terms of the ductility in these three directions. So, it is possible like limited ductility or the deformation capability, and in certain directions can also trigger the fracture when the deformation is being carried out. Or we know that when metal is subjected to the plastic deformation, we know that from the stress strain diagram, okay, what we get, different metals respond in different ways. Okay, like this. So, for the same strain, same plastic strain, they may behave differently. They say this is the magnitude of the plastic strain. So, one is getting hardened little less as compared to the another metal which is getting hardened more. The thing is, so this is what is checked through the work hardening exponent or strain hardening exponent. So, increase in the due to the plastic deformation in course of the rolling, the metal gets hardened, and this of course the yield strength is also increased, but this happens at the cost of the ductility, that is the percentage elongation, and also the toughness. So, these two properties are compromised. So, when the material is subjected to the plastic deformation, especially under the ambient condition like the steels which shows reasonably good strain hardening capabilities. So, when these are getting deformed, for they are subjected to the plastic deformation during the rolling. So, they will get strain hardened, means yield strength will increase, hardness will increase, but at the cost of the ductility and at the cost of toughness. So, if the material is losing its ductility, means its ability to get deformed, get elongated, that will be lost, and eventually it will show the cracking. Say for example, if one of the metals show the stress strain diagram of this kind, another metal shows of this kind. So, which certainly indicates this metal B as compared to the A in a stress strain diagram shows that this is the kind of a strain that can be induced prior to the fracture, while for the metal A the strain that can be induced is limited. The point is the different metals show the different level of ductilities, different capabilities in terms of the elongation that can occur, but when the metal is getting strain hardened, ductility is compromised, and if that is happening, it will show the cracks or even the fracture. Okay. So, this increased cracking tendency can also be due to the strain hardening. So, that we will come to know when we will be checking like what is the hardness and strength of the material before deformation or after the deformation. This can also be one of the regions where the thermal cutting is inducing the hard zone formation. Let us say this is the steel plate and suitable heat source like the plasma arc being used for cutting along this line. So, the metal which will be in vicinity of this line of cut, that will be heated to the high temperature. So, that is high temperature, say at this cut edge A and cut A and a little away from the cut edge B. Two different thermal cycles will be observed like this. Okay. So, what is happening here? Like thermal cycle, if we see thermal cycle A. Okay. So, here this is the temperature and this is the time on the x axis, and on y axis we have time, temperature. So, here what it shows, the rate of heating. So, it is basically the thermal cycle during thermal cutting will be showing the rise in temperature first, then the peak temperature, thereafter the cooling zone. So, the heating zone and cooling zone and the peak temperature, these are the three things that we can obtain. There are a lot of other information also can be obtained. So, if we see the rate of heating is very high and rate of cooling is also very high, if we can take the point A along the cut edge. If we take the point B, then the rate of heating will be slow, rate of cooling will also be slow, because this is little away. Okay. So, this is thermal cycle for B. So, peak temperature is also lower, rate of heating is slow and rate of cooling is also slow. So, the thing is, metal away from the cut edge will be subjected to the different kind of thermal cycle. So, usually what happens in case of the hardenable steels, the zones which are experiencing the higher cooling rates after heating, they will be getting embrittled. This embrittlement, they will be getting hardened due to the structural transformation. Okay. And that structural transformation increases its hardness. Of course, it will be decreasing the ductility and in making it more brittle. So, about this we will talk in the next few slides, how this will be happening. Then the compositional heterogeneity in the steel. So, obviously steels have lot of impurities and traces like sulfur, phosphorus, and there can be other kind of the allying elements which are segregated. So, vanadium, niobium, if these are not uniformly distributed, then their localized presence, even the carbon. So, their localized presence will be making the steel significantly different in terms of and heterogeneous in terms of the structure, in terms of the mechanical properties. And if that is had, you see this localization of the certain impurities, if it is happening, this will be making the steel more sensitive for cracking, more embrittling. Okay. Like presence of nitrogen and sulfur deteriorates the ductility and makes the steel more brittle. Additionally, there is one more possible aspect, like a steel which is incoming steel is not having the equaxed grain structure, but it is a banded one, say like few perlite, few ferritic grains, okay, as per the carbon content, okay, in the steel. So, this is the kind of the equaxed grain structure. Okay. And so, this will be offering you very good combination of the structure and properties. But what happens if the weak phases get segregated, weak phases get aligned at a particular location and forming a particular kind of the band, then this will be promoting the no sensitivity cracking tendency. So, in that case what happens, like the one strong phase, then weak phase, strong phase, weak phase, like that, SV, SV. So, this is the kind of alternate layers is possible. So, when we have the band of certain phases selectively in a particular zone, then we call it as a banded structure. So, instead of the equaxed structure, if the steel is having a or metal is having the banded structure, then this will be offering the great tendency for the cracking. Okay. So, if the steel or the metals having the banded structures, that will be showing the cracking tendency. So, the steel which was showing this cracking tendency was analyzed, and it was found that carbon is say 0.19, sulfur and phosphorus both are beyond the acceptable limits, Usually 0.005 is the normal acceptable limit. So, this is significantly greater than the acceptable limits. Silicon is lower than what it should have been. Vanadium is also high, as and other elements are there as a traces. So, considering this, manganese is say 1.5. So, considering this, it is possible to calculate using the standard formula for carbon equivalent. We can determine that where is the carbon equivalent, what is the carbon equivalent. So, say assuming carbon content is 0.2 and carbon equivalent say 0.4 to 0.5. If this is the kind of scenario, then the steel will show great hardening tendency when subjected to the thermal cycle. Okay. So, for cutting we can use variety of sources. It can be gas cutting also, it can be plasma arc cutting, okay, and it can be laser cutting also. So, these sources are significantly different in terms of the power density, say 100 to 1000 watt per mm square, say plasma cutting like 10 to the power 4 to 10 to the power 6 watt per mm square, and the laser say 10 to the power 8 to 10 to the power 10 watt per mm square. So, there is a great difference in terms of the power density. When we use a high power density heat source for the melting purpose, for the cutting purpose, what happens, or the rate of heating is very high, it requires very less amount of heat, and so it offers the very rapid cooling rate. Why? Because cooling rate is inversely proportional to the heat input that should be given, and heat input that is needed for cutting or for the welding purpose, that is found H net desired for cutting or welding purpose, that will be inversely proportional to the power density of the heat source. So, lower the power density, higher will be the heat input that will be required. Okay, when we deal with the high power density, the thermal cycle observed is like this. When we work with the lower power density, it requires greater amount of heat, and the rate of heating is slow, rate of cooling is slow, peak temperature may be corresponding to the fusion, that may be same for both the cases, but there is a difference in the way by which heating is taking place and the cooling is taking place. So, difference will be there in terms of the heating rate, cooling rate, peak temperature is same in both the cases. So, this difference in the heating and cooling rate will be bringing in lot of difference in terms of the property changes. So, that is what we can understand. If say typical for eutectoid steel having 0.8% carbon, if you try to understand using the CCT diagram, continuous cooling transformation diagram, what happens when the steel is subjected to the from austenitic state. Okay. The zones which are being cut, say this is the steel plate and cutting is being done along this line. So, the zones which are falling in vicinity of the cutting edge, they will certainly be in austenitic state. So, what happens when the austenite is cooled slowly? What we get? We get the coarse pearlite. If it is cooled little fast, we get the fine pearlite. If it is further fast, then part of the austenite will be transformed into the pearlite and remaining will be transformed into the martensite. If the cooling rate is greater than the critical cooling rate, then whole of the austenite will be transforming into the martensite. So, this is the kind of critical cooling rate desired for 100% transformation. So, if we compare, cooling rate will be lower for the gas or plasma cutting as compared to that for the laser cutting. Okay. So, accordingly there will be difference in the kind of phases which will be found. If our the phases are pearlitic, martensitic or fine pearlitic, then the hardness will be little lower as compared to the case when 100% martensitic transformation takes place near the cut edge, and that will be leading to the embrittlement of the cut edge significantly, and which will make the deformation and forming of the steels. We have seen there are a lot of impurities in form of like phosphorus, sulfur, nitrogen, maybe hydrogen also. So, when these impurities are present, of course, there is a silicon and manganese as well. So, when these impurities are clubbed and combined, then their effect on the properties can be checked. So, KTH is one of the typical property. Okay. You might have heard the fracture toughness FT, which shows the resistance to the cracking. There are multiple parameters which are used as a measure of fracture toughness. So, stress intensity factor K is one of the parameters which is used to quantify the fracture toughness. Then there are other measures like crack tip opening displacement and J integral. These are other parameters which are used for checking the fracture toughness. So, if we see the K is the fracture toughness, okay, and there is a threshold value of the fracture toughness above which the things will be getting cracked and crack will be propagated catastrophically. Okay. So, what happens to the fracture toughness threshold value of the fracture toughness or theoretical stress concentration factor, like say with the changing proportion of the impurities like phosphorus and sulfur, what happens to the steel? Like when the percentage cumulative percentage of the phosphorus and sulfur is lower, the stress intensity factor KTH is significantly high as compared to the case when the concentration of these impurities is high. So, increasing concentration of the phosphorus and sulfur makes the steel more crack sensitive, okay, because of the reduction in stress intensity factor. Stress intensity factor is one of the fracture toughness parameter which indicates how much resistance the material will be offering against the crack propagation. So, if the K value is low, means resistance to the crack propagation will be low and the crack will be propagating and nucleating and propagating very easily as compared to the case when the fracture toughness is high. And the same thing we can also see, like when we take into account the manganese and silicon also along with the phosphorus and sulfur, then also a reduction in the fracture toughness is observed. So, these the dots indicating the points corresponding to the, like say the steel had the cumulative phosphorus and sulfur content corresponding to this, which means the steel had lower fracture toughness, okay, as compared, and similarly the steel also showed the lower fracture toughness when we took the manganese and silicon content into account. Okay. So, this significantly lower fracture, the steel on its own may be having like say 80 or 100 the fracture toughness in terms of the stress intensity factor, but when the concentration of these impurities is high, then this decreases the fracture toughness significantly. Means if there are defects and discontinuities, then under the tensile stresses those will be propagating very easily and causing the opening of crack or even fracture. Okay. So, higher concentration of these impurities can also be attributed to, or one of the possibilities which can lead to the cracking of the steel when subject to the deformation. Okay. So, how to relate the carbon equivalent with the steel hardening and the cracking tendency during the thermal cutting or welding. Okay. So, carbon equivalent CE takes, it shows the combined effect of various elements similar to that of carbon. So, that is why it is called carbon equivalent. So, what it accounts like carbon weight percentage as it is, then manganese weight percentage divided by 6, chromium, molybdenum and vanadium, sum of all these three elements divided by 5, and weight percentage of nickel and weight percentage of copper divided by 15. So, for this steel composition, when the carbon equivalent was calculated, it was found to be around this, okay, which is around say 0.45 to 0.5. Okay. So, that is what if the two samples were analyzed, these were in this zone, okay, which shows so this is the carbon equivalent thing, and for a given carbon content say it is 0.19 or 0.2. So, accordingly we can locate where the steel will be falling. So, if the carbon equivalent and the carbon content, if the combination of both is seen, and based on the carbon percentage and carbon equivalent, this entire Gravely diagram shows the three different zones. What it shows, if the carbon content is less than say 0.15 or so, and then it is easily weldable for entire range of the carbon equivalent. But when the carbon content is more than 0.15, then based on the carbon equivalent we will have the second zone. This zone corresponds to the careful welding or careful cutting, which means the metal must be preheated in such a way that the cooling rate is reasonably low to avoid the embrittlement and hardening. When the carbon content is high and carbon equivalent is also high, that will be forming the zone 3. This is the zone 3, which means in this zone what will be, this zone will not be easy to cut or easy to weld. Why? Because it will offer lot of embrittlement and hardening, which will increase the cracking tendency significantly. So, when the steel was being cut without preheating, like say the steel is being cut, say the air plasma cutting along this line. So, this line is expected to offer you the hardening, okay, because of carbon equivalent 0.45 to 0.5, okay, and carbon content is also 0.2. So, if without preheating, if the cutting is done, then certainly this is going to embrittle and harden the cut edge, and hardening of the cut edge, of course, that will be taken due to the paralytic and martensitic transformation encountered due to the rapid cooling if the cutting is being done without preheat. Okay. So, the thermal cut steel plates, when subjected to the deformation to roll down in the shape of the pipes, this will certainly be making the job of the deformation first difficult and increased tendency of cracking. When the steel was analyzed for microstructure, then it showed lot of banded structures, and these banded structures are known to be very sensitive for the notch or notch show greater notch sensitivity for the cracking as compared to the equaxed structure. So, the normal versus banded structure. Okay. When a steel was subjected to the NDT also to see if there is any issue, and the steel plate showed lot of the discontinuities. Steel plate showed the defects and discontinuities, and these defects and discontinuities can be the zone of the stress concentration, weakness, and can easily trigger the cracks and then open up during the rolling process. So, as far as the mechanical properties studies are concerned, mechanical properties testing of the parent metal suggested like the proof stress were in the range of the as recommended should be greater than 550. So, it is 334, 534 to 584, it little higher than the specified limit, and ultimate tensile strength showed in the range of 786 to 904 as compared to the, this is also much higher than the 690. So, what it suggests, like when the steel is there, then say if steel strength is 550 MPa, this is fine, and strength and ultimate strength say should have been 690. So, but if the steel is showing too much ultimate strength, maybe yield strength also, then it means the steel is getting hardened. You see, too high strength is also not good, especially from the deformation point of view, especially from the impact resistance point of view, because whenever it happens, the loss of the percentage elongation and the toughness is observed. So, if the steel is having too high yield strength or too high hardness, then it will be showing the tendency for cracking, reduced resistance to the impact. So, that is what was found also, like impact toughness testing of the parent metal at the room temperature was found to be in the band of 6 to 13, okay, which is significantly lower than the minimum recommended value of the 25. So, this is what is suggesting like the material is having very high strength, but very low ductility, and this is reflecting in terms of the reduced impact resistance. So, the findings are like strain aging coupled with the plastic deformation, presence of the gases like hydrogen, nitrogen and oxygen in steel, chemical heterogeneity in terms of sulfur, phosphorus, manganese, vanadium, silicon in excess amount, and presence of the crack sensitive bended structure, and a reduction in stress intensity factor due to the segregation of the undesirable elements like sulfur, phosphorus in the steel. So, what can we say? Many undesirable changes would have taken place in the steel, would have been there, led to the embrittlement, like that could have been due to the chemical heterogeneity, strain hardening, unfavorable concentration of the phosphorus, hydrogen, nitrogen and sulfur, banded structure, low toughness and very high yield strength to ultimate to yield strength ratio. And these conditions could have led to the increased tendency of the cracking due to the delayed cracking, reheat cracking and temper embrittlement during the steel fabrication. Okay. So, now I will summarize in this presentation. In this presentation, I have talked about one typical case study in which the high strength steel was being used for fabrication of the pipes through the deformation and welding approach, and it was observed like during the deformation the cracks were observed and cracks occurring during the rolling on the external surfaces. So, it was required to investigate and multiple reasons were found for that. Thank you for your attention.